Welcome back to Physics 152 Online. We're going to finish our section on simple DC circuits by looking at what's called an RC circuit. And that's because the circuit has both a resistor R and a capacitor C, along with, in this case, a power supply. And so what the resistor does in this circuit, and it could be a circuit where the capacitor is being charged up, where it initially doesn't have any charge on it and it goes up to a maximum, or it could be a circuit where the capacitor is already charged and it's discharging through a resistor when we close a switch. But in either case, we can understand the phenomenon very nicely quantitatively using Kirchhoff's voltage law and some simple calculus that you already know. So let's look at this charging circuit. We have a switch, we have an EMF, an ideal voltage source, and then a capacitor, but when current begins to flow from the power supply to the capacitor plates, in order to charge it up, it's going to pass through the resistor. And so the resistor slows down the rate of charging. So when we close the switch, then that allows current to flow, and you can see the direction because of the potential difference across the battery, plus and minus. Positive charge will flow clockwise in this circuit, and now we have a completely closed current loop, and that's at time t equals 0. So we can immediately write down Kirchhoff's voltage law. I will go around, in order to do this, I'll go around this circuit in the clockwise direction. You can see that current will flow through the resistor going down, so the high potential end is the top, the low potential end is the bottom. And that means as we go around this loop, we have positive epsilon, and then we have negative I times R, and then across the capacitor, remember that there's Q over C. The voltage across a capacitor at any individual point in time when there's a charge Q on it is Q over C, and you can see on the capacitor plates, right, that positive charge builds up on the right-hand side, negative on the left-hand side, so we're going down in potential as we go across the capacitor. So that's minus Q over C, and that has to equal 0 because that brings us back to where we started. So that's the voltage law, and what we want to do is try to solve for the charge as a function of time. We would like to have an equation that tells us how rapidly the capacitor charges up. Now we make a substitution. The current is the rate of change of charge, and in this case we have to think about the sign because it depends on whether the charge on the capacitor is increasing or decreasing. In this circuit, when we close the switch, Q is increasing, so dQ dt is positive. The reason we have to think about that is I in Ohm's law is always defined as a positive quantity, and so we want to make sure that the dQ dt is positive here. If it weren't, if we were dealing with, let's say, a discharging circuit where the charge was decreasing with time, we would have to insert a minus sign into that equation. So making that substitution for I gives us this equation, and now what we can see is we have a very simple differential equation because the variables are Q and time t. Everything else in the equation is a constant. So we should be able, with a clever mathematical technique, we should be able to solve for the charge as a function of time. So we solve for the derivative, dq dt, and then we look at the right-hand side, and as I mentioned just a minute ago, we've got a collection of constants, but then Q. So the rate of change of charge, the charging rate for the capacitor, depends on how much charge is already on the capacitor. The more charge on the capacitor, the slower the charging rate's going to be. But how do we find dq dt in some kind of simple analytical form? What technique do we use? Well, we've done this before. And the technique is called separation of variables. We have two variables, Q and T, so we want to get all of the terms with Q on one side of the equation and all the terms with T on the other side. And we accomplish that. Let me just step back a moment. There's the equation. We accomplish that by dividing both sides by epsilon minus Q over C, and then multiplying both sides by dt. So when we do it, we get this result. And now we've separated the variables. On the right-hand side, we only have time. On the left-hand side, we only have charge. So we're ready to integrate. We can integrate both sides of this equation from the initial value of the charge to the final value, and that will be on the left-hand side. On the right-hand side, it will be from the initial time, t equals 0, to the final time. And that should with a little bit of calculus and some algebra, give us our answer. Now I changed in the integrand on the left-hand side, I changed it to Q prime simply because my upper limit I want to be the maximum charge, and I'm going to use Q as the symbol for that. The right-hand side, same thing. T will be my final time, so I'll call the variable T prime when I'm doing the integral. So the variable on the integration on the right-hand side is simple, right? The integral of dt prime from 0 to t is just t. The left-hand side, we might have to do a variable substitution in order to do that, but it's very simple, and you can see when you do that kind of substitution that you end up with a natural log. You end up with a minus sign because there's a negative q in the argument, but this becomes minus c times the natural log of epsilon minus q prime over c evaluated between the limits of 0 and q. And be careful when you substitute this in. What we do is we're going to have the log of epsilon minus q over c, that'll be the upper limit, and we subtract not 0, right, but we subtract what we get when we plug in 0 for q, and that will be the log of epsilon. All right, so be careful that you substitute in both the upper and the lower limits. So when we do that, first of all, I can take the divide both sides by minus c, and that will give me on the right-hand side negative t over rc. And then the left-hand side is just the difference of those two logs, and when you have log a minus log b, you can make that the log of a over b. So I've already skipped a step and simplified this a little bit. Now we've got a q inside the log. What we'd like to do is get rid of this log and solve for q. How do we do that? We take each side and raise e to the power of each side, because e to the log of something is just equal to that argument. So what we end up with then in one step, you can see that on the left-hand side, e to the log of the parenthesis term just gives us the parenthesis term, and on the right-hand side, e to the minus t over rc is what we get. Now it's just a matter of multiplying both sides by epsilon, doing a little bit of algebraic manipulation to solve for q, and q will be a function of the time that's in the exponential term. So here is our result. Q of t is equal to the capacitance times the voltage on the power supply times 1 minus this exponential term. And if we were to graph that, Q versus t, we see that Q starts off at t equals 0. We have 1 minus 1, or 0, and that's 0 charge when we close the switch, but the charge rapidly builds up in this sort of exponential approach to the maximum value that it has, which is c times epsilon. And that happens because at very, very large time, e to the minus a large value is going to be close to 0. And so the final q, the maximum q, would be just c times epsilon. And the capacitor gets closer and closer to that as we let the time go on. Now, in order to simplify this expression, what's usually done is to define that term r times c as a term tau, and we call that the capacitative time constant for this circuit. It's not the time when the charge reaches its final value. That would only happen rigorously at infinite time, but it's the time at which we can say that the capacitor is mostly charged. It's more than halfway, and it's just a convenient value to calculate so that you can say, all right, for a particular value of resistance and capacitance, if I multiply them together, that gives me the time at which the capacitor is pretty significantly charged up. And I might want to wait 2 or 3 time constants in order to assure that it's very close to its final value. So that is a very nice solution using what we know about Kirchhoff's voltage law and also simple calculus. Now let's do one more thing. Let's calculate what the current is in that circuit. And we just have to differentiate the charge function to get the current function. So d by dt of this q of t that we calculated on the previous slide gives us I, and that's a pretty simple calculation to do. The first term doesn't have any time dependence. The second term we pull down a factor of negative 1 over rc. The negative 1 over rc gives us, the c will cancel out, and we end up with epsilon over r times the exponential. All right? And this is also useful to plot. And notice what it tells us. Initially, at time t equals 0, the current has a maximum value of epsilon over r. Think about it. In our original circuit, when we had the resistor and the capacitor, well, that would be the current you would get if you simply took the capacitor out of the circuit. and simply had a voltage epsilon applied to a resistor R. So initially, the current is at the maximum value predicted by Ohm's law, and then as time goes on, the current exponentially decays towards zero. And we can see again, at a time t equals tau, or RC, we can see that the current has fallen significantly from its initial value, and it's well on its way toward the final value of zero. But this, I wanted to emphasize this because it shows us something very important qualitatively. If we're analyzing a circuit that's got resistors and capacitors in it, in that kind of a circuit, the capacitor initially acts like an element with no resistance because there's no charge on it. And as charge builds up on a capacitor, that opposes the flow of more charge onto it because of the Coulomb repulsion. So initially, when there's no charge on it, the capacitor could be mentally replaced with just a wire with no resistance. And that's why initially, just at the very instant where the switch is closed, the current has the value predicted by Ohm's law. But then, of course, as charge builds up on the capacitor, what does the capacitor do? It gets closer and closer to its final charge, so current flowing towards it gets smaller. And so at very long times, the capacitor acts like a circuit element with infinite resistance. And so if you replace that capacitor with an infinite resistor, there wouldn't be any charge flowing at all, no current. So that can help us, and there's a couple of homework problems like this where it's helpful to understand this basic concept in order to know what the initial behavior of a circuit will be and what its final behavior will be after a long time. So that is resistor-capacitor circuits, simple introduction to it, and I will see you in class.